Okay, there's the static cling girl. And here's another one. This device, that kind of silvery looking sphere that she has her two hands on, that is called a Van de Graaff generator. And it's a classroom sized Van de Graaff generator. It generates static electric charge. They use big ones for atomic physics research. But little ones, like, big ones where the sphere is about 10 meters across, and you could barely fit it into this room. And those we use for accelerating atomic charges and basically make what we call an atom smasher. But this one is just big enough that you can get, if your hair condition is right, you can get your hair to stand on end like this young lady. And we're going to try to get that demonstration for you next Tuesday. So females in the audience, if you have hair that's really thin, really light, and if you want to try this, now I can't do it because my hair is so curly. So it's pretty much whoever has, if you have straight hair and it's fairly light, come to class on Tuesday, but try not to put any hair stuff in your hair. All that goop, conditioner and stuff like that. And if you come with just good clean hair, fairly dry, we might be able to do the same. And we've done something as good as this before over in business administration. We got it going really good one semester. All right, we'll try to do that next Tuesday. Now, you'll have some homework over the weekend. And by the way, the homework over the weekend related to today's lecture is going to be another brain burner. The first look at one of the other brain burners of the semester, the electric charge array. So let's get down and talk about static cling, which this little shrimpy kid is having fun with. We talked about amber. We talked about magnetite last time. And we talked about tribolelectricity. Our current theory of charge is pretty solid. Relative to the days of the ancient Greeks, they didn't really know why amber behaved the way it did. They knew it was something. It took us, centuries, millennia to figure it out. Here's the triboelectric series again, and here's another example. Steel is considered neutral. Let me get my gigantic cursor. Okay, so steel is considered neutral. If you rub something made of rubber on your hands or your skin or something like that, the rubber will become negative. It'll get excess electrons. And then your hands will become positive. It'll be missing electrons. So you don't get extra protons. What happens is you're stripped of a few, relative few electrons. And so your charge is a little bit positive. All right, so that's the triboelectric series. We've talked about a couple other substances. Now, we're going to talk about the electromagnetic interaction, and one of the guys I want to mention to you is Michael Faraday. In the year 1830 and the year 1831, Michael Faraday discovered something called electromagnetic induction, which is how we get electromagnetic generators. So if you have a generator at home for use during a hurricane or any other time, it operates on the principle that Michael Faraday discovered. Alex, question. The triboelectric? No, but you can go to it on YouTube later. I want to keep going. And Alex, it's not necessary to copy it all down. It's necessary to remember that it's there, and you can go and copy it later. Okay, and similar tribolelectric series was listed for Tuesday's lecture. Michael Faraday was an interesting guy. So I don't have any notes in the slide here, but I'll just give you verbally some of my understanding of Michael Faraday. Never knew calculus, never learned calculus. He was not one of these guys like physicists are in this day. If you want to get an education in physics, you pretty much, even if you're only going to work in the laboratory, you still have to go through the boot camp of taking a bunch of calculus, a ton of calculus, I should say. But in his day, the early to mid 1800s, a lot of guys did that, but he didn't do it because he was from England and moved to London. He was the son of a blacksmith. Now, over there in England, they have a very strict, especially 150 years ago, they had a very strict and tight social class structure. So a blacksmith becoming a scientist, becoming a famous and well-rewarded scientist was like a miracle. Very unusual. Very interesting guy, Michael Faraday. He was very humble, and the best scientists are usually that way. He was very humble. The Queen of England, Queen Victoria, wanted to honor him, and one of the ways that they do that over in England is they make you a knight, Sir Michael, or they make you a lord, Lord Michael. And the guy that we named the Kelvin scale after, his real name is William Thomson. He's from Scotland. He took up the name Lord Kelvin after the name of a river, the Kelvin River or the Kelvin Brook, or whatever it's called up there in Scotland. And he became a lord. He did take the honor. The Queen, at nearly the same time as Michael Faraday. They may have heard of each other, talked to each other from time to time. Kelvin became a lord of the realm. Michael Faraday probably could have been if he had wanted to, but he was one of these guys that, I don't want to be on the front pages. I'll just hit home runs. Put somebody else, put the second baseman on the front page. He doesn't have any friends. Let him be on the front page today. And you've seen guys like that. The pitcher throws a shutout and all the reporters want to talk to him. And the pitcher will say, well, don't look, I threw the shutout. Yeah, it was good. But it wouldn't have happened unless I'd have had that shortstop back there, catching those grounders and putting guys out. I couldn't have had a shutout with that. Or a no-hitter. And that's the way Michael Faraday was. I mean, he was like Mr. No-hitter. I mean, if he had been in baseball doing the things he did in physics, they would have called him, they would have named, Cy Young would have named himself after Michael Faraday. The Cy Young Award would have been the Michael Faraday. That's the way he was. He was gigantic. He was brilliant. And he's the one that figured that the observations everyone had noticed about magnets and magnetite and the other over here, the things that people, the tribolelectricity, the static cling from amber, he's the one that figured they're both the same thing. They're both part of something called electromagnetism. This is the guy that figured it out. And he did that by figuring out how electromagnets generate electric current. The movement of electrons is coupled to the changes in the magnetic field for instance, of an electromagnet or a regular bar magnet or anything else, piece of any kind of magnetite. And in that discovery, he noticed a very small effect in the lab about the year 1830, 1831. And then he put it all together in his mind and he figured out it's because of what the magnetic field is doing, coupling to the behavior of electrons. In other words, amber. Magnetite and amber were interacting, and he's the one that figured out how it all works. Now, the guy that came after him, here's another name for you to put down in your notes. James Clerk Maxwell. He is a guy a little bit younger. When Michael Faraday was getting old, James Clerk Maxwell was just a young man. He built on the experimental work of Faraday. Faraday figured out, he wrote books, but he didn't write any math, not much math. He probably did proportions and stuff. I haven't read his book lately, but he wrote all kinds of stuff. Maxwell, yeah, he knew buku calculus. He's one of these guys that went to Cambridge and aced everything. Okay? But he was not a big, the guys that do the most talking, I mean, you've probably seen this in a lot of areas. The guys that do the biggest talking are sometimes the guys that have the least to talk about. And the guys that do a lot don't always, blab about it. And this guy was similar. Mathematicians may flatter themselves that that's a misspelling there, I just noticed it. Mathematicians may flatter themselves that they possess new ideas which mere human language is as yet unable to express. Let them make the effort to express those ideas in appropriate words without the aids of symbols. And if they succeed, they will not only lay us laymen under a lasting obligation, but we venture to say they will find themselves very much enlightened during the process, when it will even be doubtful whether the ideas as expressed in symbols had ever quite found their way out of the equations and into their minds. And James Clerk Maxwell is a physicist that figured out the mathematical theory of electromagnetism. And we still study his equations to this day, Maxwell's equations. There's 4 of them. To really understand him, you need a bunch of calculus. So we're not going to go into Maxwell's equations in this class. But as a person, yeah. And notice that slight little dig, Anna, that he's putting on the mathematicians. Yeah. Find their way out of the equations and into their minds. I share the same philosophy. Anybody here notice that I'm not going to put this on the podcast. I'm going to pull the microphone. Did anybody ever notice here that the math department is like run by the mafia? You take a test that the math department administers, they grade it, and then based on how they grade it, you have to take a test, or you have to take a class that they teach. Ever notice that? So that is basically how the math department gets buku money to hire buku professors and instructors and make you guys, Caroline. And I watched Caroline's, you're in college algebra, right? Yeah, so she's in college algebra right now. Anyway, so old Maxwell here is, now let me get back to the podcast. Maxwell was giving the business in this quote to the mathematicians. But he's the one that figured out the mathematical structure. Now, there was other guys along the way. One of the most famous guys is J.J. Thomson. And this is the guy that if you've ever heard of the Thomson twins, this is the guy that inspired the Thomson twins into existence. He, in about 1896, he was experimenting with this thing they had found, the mysterious cathode ray, that if they had a charged metal plate, a pair of charged metal plates, they could get rays to flow from one plate to the other. They thought they were like light rays. They couldn't see them, but they could see their effect. And so the cathode ray, they could make it so that if it hit a piece of glass, the inside surface of which had a thin layer of phosphorescent paint, then that glass would glow. And that is still how big glass television sets work. The CRT computer display works on the same basis. And this device down here at the bottom of the slide shows you that. He used parallel metal plates, one positive and one negative, and he was thereby able to determine that the cathode ray was a negatively charged particle that became named the electron, and that it had a very precise and measurable ratio of mass to charge. He was not able with this device here, here's the cathode down here, letter C, that's where he generated the cathode rays. He could not measure the mass of the electron or its electric charge, but he could measure the ratio of those two quantities, the charge to mass ratio, and he found that it was very, very small. And in this gooseneck part of his device, it's a big glass tube, specially blown, pure glass, with attachments above and attachments below, where you could, they had wires coming out here, and then they evacuate, they pump out all the air, so it's all evacuated. So there's no atmospheric atoms or molecules of oxygen and nitrogen in there to make the cathode rays do anything else except what these two metal plates. Here are the two metal plates. And one of these metal plates is supposed to be positive, one negative. And here's a kind of a blow up of his device. Now this doesn't have the glass tube drawn in. The previous slide does. And what he did was J.J. Thomson accelerated F equals ma, his cathode rays through the tube and in between the positive and the negative plates. Now he knew that if it was positively charged, it would dip downward a little bit. And then in this, now here's actually a piece of the tube that I did include. This is the part that has the phosphorescent green paint on it. Okay, so if this thing is this mysterious cathode ray is positive, it'll accelerate forward, and then when it gets between the positive and negative plates, if it's positive itself, it'll dip down towards the negative plate. And then you'll get a blast of green light down here in the lower part of this glass tube. Similarly, Jonathan and Logan and all you SSG leaders, similarly, if it is a negative particle, Hector, this mysterious cathode ray, then it'll dip upwards slightly, depending on, how big a battery. So you have these two metal plates, you connect them to a battery. You connect one end to the positive end of the battery and the other end to the negative end of the battery, and you shoot your cathode ray through and see what happens. Well, this is what happened. It deflected upward, bang, and you got a burst of green light above the center line. And what that tells you is that you have a negative particle because it's trying to get closer. It accelerates through, and then when it gets between the plates, it gets a little bit of upward acceleration. And so the green burst of light here is above the center line, and that shows that it's a negative particle. So he was able to measure that it was negative, and he was able to measure the ratio of electric charge to mass, the charge to mass ratio. And here's a picture of an old type. You may have seen these. I think they still make them. I actually have an old TV of this kind in my office over the Physical Sciences building that I bought back in 1995 so I could watch the Green Bay Packers. But this business of steering electrons, we have special phosphorescent paint now that if an electron hits it, it'll glow green. Another kind of paint, it'll glow red. Another kind of paint, it'll glow blue. Red, green, blue. And that's the RGB color system that many computers still use, even though we're on flat screen technology for the most part. Anyway, so that's what Thomson was able to measure. He thought that an atom, in his day, 1896 and around there, the turn of the previous century, so this is about 120 years ago, they were pretty convinced that atoms existed, atoms and molecules. They didn't know what the structure of it was, but Thomson said, I think that it's a positive blob of matter, and these negative electrons are kind of embedded in it, kind of like raisins inside of a cake, which I guess if you're from England, you eat cakes that have raisins, in his day, that have raisins embedded in it. Let's see, you know what it'd be like? It'd be like, what's that stuff? Mint chocolate chip ice cream. You know? So that the chocolate chips are embedded in the green ice cream. That's a pleasant thing to think about. Oh, sorry. I just got flagged by, what's your name again? Rachel over here in the front row. Okay. Well, let's stop talking about ice cream. Let's just talk about, this will take away your appetite. This is a photo, this is the actual device he used. Okay. The metal plates that he used were in here, inside this thing. Here's the cathode, and then here's the target over here. And so that's what, you can't really see it, but there's a thin strip from up here to down here at the bottom of this sphere on the right side, a thin strip of paint that will glow. Now, one of his contemporaries was a guy named Rutherford. And here's a picture of Rutherford. And Rutherford, Professor von Rutherford, discovered something even more interesting. And his experiment concerning atoms and electrons and stuff was a little bit different. They weren't using the mysterious cathode rays. He was using the mysterious alpha particles. In his day, they knew that certain elements like radium would emit radiation that could be observed and measured, kind of like what J.J. Thomson did. And they didn't know really what it was. They knew that radium, for instance, was radioactive, but they didn't know what these alpha particles were, or alpha rays they thought they were. And so what he did was he said, all right, I'm going to take a little tiny chunk of radium or something that puts out a lot of alphas, and I'm going to collide it with a very thin gold foil. Now, and so that the gold foil goes bang. Now, the reason that he used gold foil, did you know this? Gold can be machined or pounded, milled, so thin that it hangs together as a piece of metal. It'll conduct electricity, but you can see through it. Did you know that? And so gold foil, you can make it extremely thin. So he said, let me use a fairly thin, so he didn't use a gold nugget. He used a piece of gold, they pounded it out to very thin levels, and they jammed those alpha particles into it just to see, you know, and that's typically what physicists do. You know, they bang something into something else and look at what happens to all the smithereens that result. Okay? And so this is the device that he had. Here's kind of a schematic diagram of Rutherford. This is Rutherford's experiment. And in physics grad school, every a grad student redoes this experiment because there's an enormous amount of physics in this. Now, this picture shows you down here in this kind of gray cube a source of alphas. So this might be like a piece of radium. You know, just a couple grams of radium would be enough. And then it goes through something called a collimator made of lead. Now, the lead will prevent the alphas, some of the alphas. But if you put just a little teeny slit in the lead collimator, you'll get a nice narrow beam of alphas. And you can get it to go where you want, Melanie. Right? And so he wanted it to go right through this detector here. And here's the gold foil. And then around the detector, or around the foil, here's his phosphorescent screen, this kind of dark gray cylinder. And when those things, yeah, zinc sulfur, okay? When those things, when the alphas hit this gray kind of cylinder out here, they came out at different angles and it caused it to glow, and they would try to take account of that, right? And they counted up, you know, how many went straight, like these ones right up here, they pretty much went straight through. Okay, it's thin gold foil, so there's some of them are just going to plain miss. Some of them deflected off in this direction. That looks about 30 degrees over there. Some of them deflected over this way. This is about a right angle. It comes in this direction. Everything, if you have a good collimator, you have a good thin beam, everything will come in at the same direction. So if you figure out the location of the impact right here in the lower right of this dark gray cylinder, then you can figure out the angle. So this one looks like it's about a right angle. But the most important thing that he found, Courtney, was this. This one right here. They scattered, or they ricocheted at something greater than a right angle. Okay, so it wasn't like you know, kind of going straight through. It wasn't easing off by 30 degrees, not even 90 degrees. It went through and it ricocheted backwards. This is what we call backscattering. Very important vocabulary term for you. Because backscattering means that you have electrostatic repulsion, electrical repulsion. And that had profound influence on the theory of the atom. You know, Rutherford was thinking about raisins in bed. He must have been hungry. You know, it must have been late at night and no pizza delivery in Cambridge. And so he's thinking about his mom's raisin cakes or whatever he was thinking about. But Rutherford said, I don't think it's that. And this is what they expected. They expected to see, you know, the alpha particles kind of breezing through there, straight on through. But what they found was this. And so this upper picture here, it's kind of purpley on the screen. It's red on the actual YouTube. This picture up here, this is basically Thomson's view. This is like an idealized view of his mom's raisin cake. Down here, this is what they figured must be happening, because you can't get backscattering. Like this one right here, this arrow that dips back almost 180 degrees, that's backscatter. As long as you're dipping back more than 90 degrees, this one's about 170 degrees. You get 170 degree backscattering, the only way that makes sense is if something in there is positive. Because they knew the alpha was positive. They knew that. The only way to get a positive particle to recoil like that is for it to meet and interact with another positive. Because positives and negatives attract. But positives and positives, if you send a positive in and it ricochets back, that means you got another positive in there somewhere. And they figured that that was something. And they did all the math and all the calculus, a huge amount of trig in 3 dimensions, and they figured out the size of the nucleus. And they said to themselves, whoa, we don't have a cake with little raisins embedded in the cake. What we have is a tiny nucleus surrounded by tiny electrons in empty space. And that's what we think of the electron and the atom as now. So let's review what we know about atoms, electrons, and protons to this day. But before we do that, can I just ask a question? Would you guys like to dismiss early today? Maybe? I mean, we could try it. Okay. All right, so here's what we think. You know, electrons, protons, and neutrons. Now, neutrons were discovered a couple decades after Rutherford made his discovery. He figured out that the nucleus has to be positive. So I put a little bag here, kind of an oblong bag of 2 protons and 2 neutrons. And then here's a couple electrons. And Rutherford said, all right, I think that what we've got here, instead of having a cake with little raisins kind of sitting in there, we've actually got a little solar system. It's planetary. We think that, he said, I think we got this really heavy positive nucleus, and we have electrons, but they're orbiting the nucleus like a planet orbits the sun. Now that's the Rutherford model of the atom. This is a model of the helium-4 nucleus. All these nuclear loads, all the atoms that we know of, all the elements, we've figured out pretty much all the different varieties of nuclei. So like gold has a lot more protons and a lot more neutrons. It's pretty heavy. Helium's really light. It's just got 2 and 2. Helium and hydrogen's even lighter than that. It's just got 1. A proton. That's it. That's the nucleus of a hydrogen atom. Okay, and this one's helium-4, and the 4 indicates that you've got 4 items. There are some. Go ahead and write down this word. I'll spell it out for you. Isotope. I-S-O-T-O-P-E. Okay. Isotope. I-S-O-T-O-P-E. A nuclear isotope is a kind of a nucleus that's not the same as the standard nucleus. And what I mean by that is, any nucleus that has only 2 protons in it will be a helium nucleus. The number of protons in the nucleus controls the element that you've got. 2 protons, that's helium. But even though helium normally comes with 2 protons and 2 neutrons, we can find, not too hard to find, helium-3, which has 2 protons and only 1 neutron. Okay, so that's an isotope of helium, helium-3. 2 protons, 1 neutron. Right? And gold has isotopes. Oxygen has isotopes. Oxygen is, the normal oxygen that you breathe is oxygen-16. That's 8 protons, 8 neutrons. But there's a little bit of oxygen-17 on Earth, and that's 8 protons, 9 neutrons. And there's also a little bit of oxygen-18 in the air you breathe and in the water, in the H2O that you drink. So oxygen-18 would be 8 protons, as all oxygens must have, and 10 neutrons. Those are isotopes of oxygen. And most, even hydrogen has isotopes. There's a special kind of hydrogen called deuterium. Let me spell that one for you. D-E-U-T-E-R-I-U-M. Deuterium from the Greek word for two, deutero. Deuterium is an isotope of hydrogen. It's got one proton and one neutron. And we can filter out deuterium fairly easily from regular water. Every glass of water that you drink, odds are that you're drinking a bunch of deuterium with it. Now, most of it's regular hydrogen, one proton, one electron. But there's measurable amounts of deuterium, and it can be filtered out. In World War II, there was a famous battleground in Norway called the Norsk Hydro plant. Up in the mountains of Norway, a hydroelectric plant. And at that hydroelectric plant, they had made a practice of filtering out deuterium flavored water. In other words, water with some deuterium in it. The nickname for that is heavy water. Write that phrase down, heavy water. Heavy water is, it's not regular H2O. It's got a deuterium D, a hydrogen H, and an oxygen O, DHO, heavy water. And it's a little bit heavier than regular water. You know, so cubic centimeter of regular water is going to be 1.00 gram. Heavy water is going to be a little bit heavier than 1.00 grams, depending on how much deuterium you've got in there. Okay, they purify it and purify it and purify it. It'll be noticeably heavier by a few percent. Now, the reason that that was a famous battle site, the Norsk Hydro plant, and there have been books and movies written about it, is because the Germans were trying to use heavy water for nuclear research to build an atomic bomb. And we found out about it. Britain and actually the Swedes, or the Norwegians, escaped from Norway, which was occupied by the Germans. They escaped, came to England and said, you know, look, we've got all this heavy water, and the Germans are taking it over. We got 90 kilograms of heavy water, and they can use it for their nuclear. And we know, everybody knew what you could do with it. It wasn't like a big secret. And even in this day, when we hear about these guys over in Iran that are causing so much trouble, they're trying to run nuclear reactors to get uranium, to refine uranium and stuff. And a lot of those reactors use heavy water as part of the nuclear reaction, right? As a kind of a side part of the reaction, just the way that the Germans were trying to do. So the British and the Americans eventually destroyed that hydro plant, and they didn't destroy the dam, but they destroyed enough of the plant that the filtration apparatus was destroyed. And otherwise, we'd be speaking German right now. Or Japanese, maybe. But we knocked them out, and then we knocked out everybody. And we figured out at Los Alamos and Oak Ridge and everything, the Manhattan Project, we won, and the world is free. Otherwise, we'd be slaves of Adolf. I don't even want to think about that. Or dead. Anyway, heavy water and isotopes. All right, here's a little IQ test for you. Frequency BB. And don't worry about the refresh key. If like charges repel, what keeps a nucleus of protons and neutrons together? Alicia, you know that the nucleus is positives and some neutral stuff, so they should be pushing each other away. I mean, electricity is not turned off. It's just, you know, but for some reason, the nucleus does hold together. Here are 4 possibilities. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Well. We got a spread of answers, and the correct answer is this one. So that drew an interesting response. So, my wonderful students, make a note of option C. The fact that Rutherford discovered a nucleus that was positive implicitly locked in this concept that there's now a third force that's neither electromagnetic or gravitational, but strong enough to hold the nucleus together against electrostatic repulsion. So those positives, they'd like to blow each other apart. They want to avoid each other. But this third force, and students, this third force is called the strong nuclear force. There's no minerals like amber or magnetite that it's named after. It's just kind of generic strong nuclear force. Now, there's another nuclear force called the weak nuclear force, and that is related to neutrons and protons decaying back and forth, a neutron decaying into a proton and an electron. But the weak nuclear force, and then this one's the strong nuclear force. Gravity, next Tuesday, I'll show you how to work out the fact that gravitation is a WIMP. You may write that in your notes. Dr. B says gravitation is a WIMP. It is so much weaker than electricity, and even weaker by far than the strong nuclear force, that you don't even, when we're doing nuclear physics, we don't factor in, we do not factor in gravitation for nuclear physics. All right, let's keep going. Let's talk about Coulomb, the scientist. Now, this is the guy that figured out the force law. Sir Isaac Newton figured out the law of universal gravitation. All right, that's one of the forces of nature. This is another one, electromagnetism. And Coulomb is the one that figured it out. He's from Martinique. He started out as a military engineer. 1776, the year of our independence. And long may we reign. He moved to Paris and became an academic scientist. So he started out as a military engineer, helping the French army. Moved to Paris. So he's out there in the battlefields and stuff, working with the French army, helping them conquer some fort or whatnot with cannons and stuff. But he's really thinking in his head, I'd like to be an egghead physicist in Paris. And he eventually did that, which is a nice break. He developed a balance for measuring very, 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 very small forces. And remember, when you rub a balloon against your shirt, you can pick up little teeny tiny pieces of paper with it, but you can't pick up gigantic, truckloads of paper. Right? So the forces are small. He developed a balance that was, it stayed horizontal and twisted horizontally. So this is the regular gravitational balance over here. You put something on the left and you figure out how many of your grams go on the right. And when they balance, when it's perfectly horizontal, then you've got, you've measured the weight. Okay, now that's gravitational. That's not what he did. He made a balance that stayed horizontal, but twisted. And Karina, the twist angle correlated to the force. He used a fiber to suspend his balance from the ceiling. And that fiber, he could calibrate, so many degrees corresponds to so many newtons of twist force or torque. All right? And so he was able to figure out forces very, very small, like the small forces that you get when you rub a balloon and pick up little teeny pieces of paper. It's called a torsion balance, and we still use it to this day. Fancier versions than what he had, but we still use the torsion balance for a lot of things. And he was able to figure out the force and the relationship between the amount of electric charge and the amount of newtons in their interaction. The gravitational interaction, universal gravitation, the size of the force, among other things, depends on how much mass you've got. Mass 1 and mass 2, and then how far apart they are, r squared in the denominator. And Coulomb figured out that the electromagnetic interaction was very similar to that. Here's a perspective view of his torsion balance. And it's kind of idealized, so that it just shows. Here's the torsion fiber right here. And so many newtons of force for every degree of twist. And so this tiny red sphere here at the end of this long rod, and in the middle of the rod is the fiber that supports it. And then over here on the other side of the bowling ball, this big dark gray bowling ball over here, the far side of it is this other red one. So if these things are charged up, if the bowling ball is charged and the little red spheres are charged, they're going to try to draw each other to each other. Okay, so here's an overhead view. So here's the two little red spheres. Go ahead and sketch this one. This is the main one to sketch. Okay, and right here, it's kind of faint, this X right in the middle. Okay, that's the torsion fiber there. Now, if we can bring something in close to the little red sphere that's charged, and if the red sphere is charged, we can get some repulsion or some attraction. All right, so let's bring in the bowling balls. Here they are. A couple 12-inch diameter bowling balls. And you could charge those up by friction. It would be very easy, but you could do it. All right, and so theoretically, if the little red sphere is negative and the bowling ball is positive, so different materials, and you rub them up with, something else from the Tribolelectric series, so you get some positives here and some negatives up here. They're going to attract each other, right? So your 2-inch diameter sphere here, the red one, gets attracted down to your big 12-inch diameter bowling ball. All right? So there's a little bit of a twist angle. All right? So if you look at it down over here to the right, these two angles will be the same. I mean, if everything's balanced and, even and symmetric and everything, those angles will be the same. And so I'm removing the original state. So here's the swing angle, this curved arrow over here to the right. Okay, and then what you want to be able to do, and what you can do if you have good equipment, measure the distance from the center of this bowling ball to the center of the little red sphere. And then once you do that, then you correlate the twist angle and the force. And you correlate the distance with the force as well. So you measure the twist angle, like 2.7 degrees or 5.8 degrees. And that tells you how many newtons of force. And then the distance tells you, how far from center of mass to center of mass. In this geometry anyways. And then from that, you can figure out the relationship between charge, distance, and electrical force. So this is the overhead view of the torsion balance that Coulomb used. And what he found out is that the interaction that we now call by his name, the Coulomb interaction, is very similar to universal gravitation. The Coulomb interaction is pairwise. In other words, it's charge to charge. So it depends on how much you've rubbed up your balloon over here, the blue one, Q2, and then this red one over here. It depends. What the heck is this? That's nothing. How did I do that? Anyway, sorry about that. Anyway, so charge here, Q1. And students, either capital Q or lowercase q is traditional or the customary symbol for electric charge. And here's the distance between them. Okay. And then his torsion balance measured the force. And a little bit of geometry and trig got him R. And then his charge up procedure gets him a measure of Q. And so in other words, how much force did you use? Distance apart. So he found that it got weaker with distance, and that the formula, look at this formula. It's just like universal gravitation. It's a constant, K, times the product not of two masses, but of two electric charges, Q1 times Q2. And then in the denominator is R squared, the distance between them. Not R to the third, not R to the 14th or any other, but R to the second, exactly. Now, it's not exactly like gravitation because there's two kinds of electric charge. There's only one kind of mass. All mass is positive. All mass attracts every other mass. Electric charge could be positive and negative, as Ben Franklin showed. Charge does not measure in kilograms. It measures, in the metric system, it measures in coulombs. In addition, electric charges can repel each other. Now, gravitation never does that. And people have tried to show, well, if you have, a mass that's negative or faster than the speed of light, they try all kinds of tricks, but we can't really seem to figure out a way to show that, yeah, gravitation could be repulsive. It always seems to be attractive. Now, a couple things about that inverse R squared force. This has R squared in the denominator. And because that is true, we say that the range of this force is infinite. We also say that the photon, which is the quantum of electromagnetic radiation, is massless. There's no mass for the photon. All right, and that is an enormous implication, physics-wise. Infinite range, massless photon. Now, once he figured out this force law, K times Q, oh, by the way, the letter K is known as Coulomb's constant. And the value of it is like 9 times 10 to the 9 in metric units. Newton meter squared per Coulomb squared. And we'll get to that in a minute. Once the force law was known, the electroscope, which is diagrammed here, became a pretty good charge measuring device. So in other words, you had a really good numerical method for measuring the amount of charge. Here's how it works. If you load some electrons into this device, the charges will move apart from each other and end up down in the extremities. And that means down here in the leaves. Now these leaves are frequently made of gold foil. Very light, but a good conductor. So there's charge at the top, and then there's charge on the two leaves of metal foil. That's the electroscope. And then if you then work out a little bit of trig with this diagram, and let me go to the next slide. Here's a kind of a side view of an electroscope. You have negative charges down here on the two leaves, and if the two leaves are the same size, then they'll repel each other symmetrically left and right, those two big red arrows. All right, so you have two forces, and because you know the force law, and you do a little bit of trig and a little bit of calculus, you can figure out, okay, if they dip out a certain degree, like 17.5 degrees, that means I have so much electric charge. If I have more than that, they go a little further out, 18.5 degrees, or whatever they go out to. All right, so this is called the electroscope. It is still in use today, fancy versions of it. And there's other ways to measure charge now. But this is one of the first ones. And this is how you can easily figure out the load of charge, either negative or positive, on a charged object. Now, I want to trot you through something you're going to see in the homework. I'm going to ask you some questions. Go ahead and sketch in this set of 3 pairs of particles. The 2 blue ones at the top are 2 electrons. The symbol for the charge on the proton is E. So the charge on an electron is minus 1e. The middle pair, a red on the left, plus 1e, that's a proton, and minus 1e on the right, that middle pair is a proton and an electron. And then the bottom pair are 2 red ones, they're both plus 1e, those are 2 protons. Now, I have a mental IQ test for you right now. Actually, it's not an IQ test, it's kind of a brain test. Which pair or pairs have repulsive interaction? The top pair, the bottom pair, the middle pair, top and bottom, all 3. Which ones repel? "20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let me see what you guys have got here. Whoa, very good. Top and bottom. Most of you volunteered for or voted for that. Very nice. These 2 in the middle, positive and negative, will attract each other. They'll have, and students, they're all these particles. I've mapped them out, I've diagrammed them out so that they're the same distance apart. So R squared in the force law is the same for each pair. The numerator is the same size. The only thing that changes is one of them's repulsive, or 2 of them are repulsive, one of them's attractive. That's the middle one, right in here. Question number 3. Da, 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 da. Rightmost proton, what's the direction of the net force? You have approximately 50-50 chance of getting this right. But if you vote for C, you have 0 chance of getting it right. A or B? D? There is no D. Don't vote for D. That's the D is the maniac detector on this question. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what we got here. Yep, right word. Now, a fair fraction of you voted for B. Wait a minute. Somebody voted for. All right, it's right word, and here's the way you want to think about it. Your target particle's here. Now the closest neighbor is that other proton, and it's pushing to the right. So make a note. The rightmost proton gets a big push to the right from the other proton. Okay. Now the electron, the blue electron on the far left, pulls the rightmost proton to the left. But the rightmost electron, Melanie, is further away. It's double the distance. And so because it's double the distance, the force is 1/4 as big. Because it's 1 over r squared. So if you double r, the numerator becomes 4 times bigger. The fraction is 1/4. So this one over here is pulling to the left, but it's not pulling with as much newtons as the middle proton is pushing to the right. Now, why am I bringing up this particular item? I'm bringing it up because this is very helpful when you're trying to figure out what molecules do. A simple molecule like H2O or DNA. The electric charges on the atoms and different parts of the molecule affect the structure, how it reacts, what it does, what kind of electromagnetic radiation it interacts with. All that stuff is determined by figuring out forces between particles like this. So, homework 18, I'll have something ready for you by lunchtime tomorrow. It'll be due Tuesday. You're dismissed. A little bit early today.